So welcome everybody to our Gamma seminar. We have the pleasure to guest today Robert Wolak from the Jagiellonian University, who is going to talk about Sasakian manifolds. So Professor Wolak, thank you very much for accepting our invitation. The floor is yours. We hear you. Thank you.
Thank you for the invitation. It's really a great pleasure to talk to physicists, something which I hope it will happen more times, let's say. So let's start with very basics. So with the definition, first there are several sections in my talk, definitions, then I will talk about transverse properties, because Sasakian manifolds can be understood as foliated manifold with a very special transverse structure. So I will talk about transverse properties and something about general basic properties. And let's start with the definition. So we are in odd dimensions. So we have a smooth connected manifold of odd dimension. Then we have a one form, a very special one form, such that when we take the differential and we take the wedge product, the suitable number of times, so that we get the top degree form, so it's n+1 form, and we require that it's non-vanishing at any point of the manifold. So actually, that eta times d eta to the nth power, it's a volume form. In this case, eta is called a contact form. Certainly, when you multiply by a function, you also can get a contact form. You see, so it's especially it's a non-vanishing function. So a contact manifold or contact structure on a manifold is usually an equivalence class. So, and there's a notion of a strict contact manifold. So when this one form is specified, not the equivalence class, but one form. So then we have a unique vector field. It's called the Reb vector field, such that eta evaluated on psi is equal to 1, but when you take this two form, d eta, and you take the inner product, it's 0. It means more or less that the differential of eta is, in the language of foliations, in the basic form. So, this vector field, non-vanishing vector field, defines a one-dimensional foliation. So this particular foliation, this one-dimensional, is transverse symplectic, because this two form is a transverse symplectic form in the language of foliations. So we have a natural splitting of the tangent bundle into the kernel of eta, d, plus the one-dimensional subbundle generated by psi. So, well, there's a lot of, let's say, contact manifolds are considered a kind of odd-dimensional counterparts of Keller manifolds, and there's or symplectic manifold, rather, sorry. To Keller manifolds, I will come later. So of symplectic manifolds, there are some very nice books about topology of contact manifolds. It's Hans Geiger's book, which I will mention at the end of it, is a very nice introduction to topology of contact manifold. So, but as geometers, they like a richer structure. So they introduced an almost contact manifold. An almost contact manifold, in fact, is a triple. We have psi, eta, and phi, where psi is a vector field, eta is one form, and phi is an endomorphism, 1-1 tensor on the manifold, so endomorphism of the tangent bundle. So what is the relation between these three objects? So there is a very easy one. Eta evaluated on psi is just 1, but phi square is equal to minus identity on the tangent bundle, because phi square is an endomorphism of the tangent bundle, we see modified by this psi times eta. So, as you see, it's a kind of odd-dimensional version of an almost complex structure. So, it is easily verified that phi evaluated on psi is 0, and when you eta evaluate on the image of phi is also 0. So, so we have a natural splitting into direct sum of the tangent. Those foliation could be understood as a subbundle, D, where D is equal actually to kernel of this one form, but also to the image of this endomorphism. So, but it's also geometers like a little more complicated. They like something involving the distances, Riemannian metric. So they introduce the notion of a kind of compatible Riemannian metric with an almost contact structure. So we have 4 objects. We have an additional Riemannian metric, but this Riemannian metric satisfies this formula. So it's G evaluated on the image by phi of any 2 vectors is the value on these 2 vectors minus this eta time evaluated x times eta evaluated on y. And the quadruple is called an almost contact metric structure. So you see, there are a lot of notions. So a remark, we have the vector field psi. It need not to be killing for the metric. Even if this quadruple G psi eta phi is an almost contact metric structure. It's a reference to some book about, later you will see it. Okay. And there is a strict contact manifold. So is it M within one form? Eta is compatible with the almost contact metric structure. You have another form, and of these 4 objects, for any 2 vectors, we have this one. And of course, eta is equal to eta prime, contact metric structure. Okay. So there is also another condition could be added. You see that this vector field, the Reb vector field, as I have said, need not to be killing. It is, so if psi is a killing vector field for the chosen Riemannian metric, we say that this structure is K-contact. So a contact metric structure on the manifold is K-contact if you see if psi is a killing vector for the metric G, and then this you see this structure M, G, psi, eta, eta and phi is called a K-contact manifold. And there is another condition. An almost contact metric structure on the manifold is normal. If the phi is 1-1 tensor satisfies this Nienhuis, we say construct the Nienhuis tensor, and phi in the standard way, like for that's the formula for the almost complex structure, and it's normal if it's equal. You see, this one is the standard formula equal to minus psi times eta xy. It's normal, so there is this, you see, a kind of correction. And a Sasakian manifold, finally, in all these tensors, you see involving, you see at the very top pinnacle of all that, all this more and more complicated structure is a Sasakian manifold. So a K-contact manifold whose underlying almost contact structure is normal is called a Sasakian manifold. So it means that for a Sasakian manifold, if this condition is satisfied, we have this quadruple of these tensors, forms tensors, etc., and phi satisfies this very special condition. Okay, which corresponds to the integrability of the almost complex structure.
Excuse me.
Yeah.
Yeah, there is a lot of definition. Could you provide like illustrative, simple examples of such structures?
Oh. Complicated. So certainly for Sasakian, it's difficult to, let's say, because it needs a lot of calculations, actually. You see, certainly you can find these in the references I will give you later, okay?
Yeah,
because
sure.
otherwise
Thank you.
it's very, so let's say, what is important here? So there are certain conditions. So for instance, certainly remember that when you take at the very beginning contact structure, so when you take a symplectic manifold and you multiply by S1, so certainly the characteristic one form corresponding to this, you see this S1, you have the definition form, let's say dt corresponds to this component S1, certainly eta, if its eta is equal to dt, then you see differential is zero, so it's certainly it cannot be such a way. So one of the conditions where all this stuff getting okay here, you see this condition here means that this bundle is very most unintegrable. So you see, it cannot contain any distribution sub-bundle which is integrable. This is one. You see, that's the idea. So on one side, you have a product, manifold, symplectic manifold times, for instance, S1 if you want to stay compact, or R if you if you don't care about it. Sorry, I'm a bit ill. Some problems with so the weather is a bit unpleasant in Krakow, I believe in Warsaw too. So it's well, so that's the difference. So and so there are two extreme cases: product and the contact. Product with a symplectic manifold and the product. So there are examples. There are certainly there are. So for instance, you can produce examples on the nil manifolds, actually. If you want to, you know, nil manifolds are the compact quotients of omnipotent groups, or let's say, or solved manifolds, solvable Lie groups. So when you look at the invariant structures, then you just reduce everything to to the properties of Lie algebras. So it's, well, one of the way of let's say, you see, coming up with examples and to test.
Javier, can I say something?
Of
Here
course.
is Manuel.
Yeah.
Yeah, concerning examples, contact metric structure are the odd-dimensional counterpart of almost-scalar manifolds. There are 16 different classes of almost-scalar manifolds and examples in each class. And there are 144 different classes of contact metric manifolds. And there are examples in any of them. And Sasakian and cosymplectic in a different way that is related with this normal structures, are the Keller counterparts in odd dimensional setting. And there is a lot of many examples.
Yes, there are many examples. Also, there is one of the rich topic of research was to distinguish between K contact and Sasaki, which is not so obvious because it's a very subtle difference. As you said, you see, K contact are almost transversal, almost scalar, and Sasaki are transversely scalar. So there are special properties. Well, it was used to produce these examples. There were some say, cohomological properties. You see, I have a theorem later on, you see, prepared to, which was used to distinguish between these structures. There was the first examples produced because it was important. So, well, there are a lot of examples, but they are not so easy to write down and to check all these conditions. So, as I said, you see, one of the ways to look at Sasakian manifold is to look at a foliated manifold with one-dimensional foliations. So you need to know something about so-called transverse structures. So there are some general information about foliations. So there are several approaches to foliations. One of them is particularly useful to the study of transverse structures, using a cocycle definition. So on the we have a manifold of dimension n defined by a cocycle. So cocycle UFG with indices coming from the same set IJ. So the UIs are form an open covering of the manifold. FIs are submersions for the you see to make life easier with connected fibers, and GIJs are a local diffeomorphism of this modern manifold N0. Could be of dimension in the case of Sasaki manifold, it will be of dimension, even dimension, but in general could be of any. So you see, when you look at it and you forget the submersion, when you just take it a local diffeo, you have a notion of an atlas, of a manifold. Okay, so it's a kind of generalization of the definition of a manifold using an atlas. So we have such a cocycle, and the kernels, the fibers of this submersions form a are submanifolds because these FIs are submersions. Okay, so and because of the third conditions, these fibers glue together in a nice way. So we have a kind of partition of the manifold into submanifolds, and it's a foliation. It's an equivalent definition to any definition you have of a foliation. Okay, but so in our images, because FIs are submersions, they are open subset of N0, of our model manifold. And we take to make life a little on one side, here on the other side, a little bit more complicated, we take the disjoint union. So this NU is not connected. It's a transverse manifold of the foliation. And these GIJs generate a pseudogroup of local diffeomorphisms, which is called is the holonomous pseudogroups associated to the cocycle U, HU, script H, script U. So actually, different cocycles define the same foliation as different atlases define the same smooth structure on a manifold. So there are equivalences of atlases, there are equivalences of cocycles defined. So I won't go into it because usually people work with just a given cocycle. You see, it's a general. You see, when you want to be very precise, exact, so you need a equivalence class. But the same is with the atlas of a manifold. Very often you just choose the atlas and forget about other equivalent atlases. You just prove the theorem using just one particular atlas. So there is a notion of equivalence given by Andre Hefliger in his paper. So there's a transverse property of a manifold, of a foliated manifold, is a property of foliations which are shared by any two foliations with equivalent holonomous pseudogroups. So when we take a Riemannian foliation, so any foliation with whose holonomous pseudogroup is equivalent to the holonomous pseudogroup of a Riemannian foliation can be made Riemannian. So what about we have a HU invariant forms on manifold NU can be identified with the so-called foliated sections of the normal bundle. That's the normal bundle. You see exterior product of the, let's say, conormal bundle, and that's the, let's say, a bit formal definition, but that's the standard definition you see one uses when working. So we have basic forms, HKMF, so all forms, K forms, such that they vanish on when you put one tangent vector field to the foliation, the form vanishes and the differential also vanishes. Actually, such forms, when you take, you see, submersion, when you have a basic form for a submersion, these basic forms come from the base. So they actually, the forms on N0 or on the image just corresponds to basic forms on IU for the foliation given by the submersion with connected fibers. So that's why it's basic. So for instance, a submersion with connected fibers defines the simplest, probably almost the simplest possible foliations, and basic forms come from the base. These two complexes are isomorphic. Okay. So as the differential, obviously, because of this condition, the differential sends basic forms to basic forms, we have the complex of basic forms with a standard differential is a differential complex, and its cohomology is called the basic cohomology of the foliated manifold. So in the language of basic forms or this, you see, basic cohomology, there are a lot of properties which can be expressed. And what is important is that in the case of as you see, Sasakian manifolds are very special. Foliated manifolds, a lot of the basic homology in the case of Sasakian manifold, or for that matter also for K-contact manifold, because the foliation is so-called Riemannian foliation, it's the question is that this cohomology is finite dimensional. So the Riemannian foliation can be characterized in a very nice and simple way. So you have a foliation, so you have leaves, you have metrics, so you have a geodesics for that metric, and when you take a geodesic and you check at one point that the geodesic at one point is orthogonal to the leaf passing through that point, this geodesic must remain orthogonal everywhere. So it is enough for geodesic to be orthogonal to the leaves of a Riemannian foliation in one point, then it's orthogonal at any to any leaf it meets. So it's a nice property which in fact characterize Riemannian foliations. So it's and what is important for Riemannian foliation, so what is also true for Sasaki foliation, the fact that the basic homology is finite dimensional. What is a little different is that the top-dimensional, top-degree basic homology can be zero, even for compact manifold. It's now for the oriented, even for oriented compact manifold, the top homology is non-zero, is one-dimensional. Then the condition for foliations, for Riemannian foliations, the top cohomology can be zero and non-zero or non-zero, but it's at most one-dimensional. But for non-Riemannian foliations, cohomology, basic cohomology groups can be even infinite dimensional. So there are simple foliations obtained by so-called suspension, which give you infinite dimensional basic cohomology. So it's related to, let's say, to invariant cohomology for say diffeomorphism. Actually, the example is related to a tori. So, so what are the? I have introduced various types, more and more complicated foliations for contact manifolds. So, what are the transverse structures? So, for a contact manifold or strict contact manifold, the characteristic for the two form is basic. So, the foliation given by the Rem vector field is transversely symplectic. But in this case, there is some problem with cohomology, but as I say, I will skip it. Okay. Okay. So what about in the case of almost contact structure? We have the following conditions for Riemannian metric. So there is a Riemannian metric for which the orbits of psi are geodesics. That the L psi eta is zero, or when you put psi into d eta is zero. So these conditions are equivalent. Of course, the 2 and 3 are obviously what is really necessary to prove is just equivalence of 2 and 3 and 1. In the case of A contact metric structure with these 4 tensors, we have the following equivalent conditions. The characteristic foliation is Riemannian, as I told you. Xi is a killing vector field. When you Xi preserves the 1-1 tensor, so L Xi phi is equal, the contact structure is K contact. The contact metric structure is K contact. So, so it's a simple. There's not really a lot to do, but still careful calculation. So you can find it in the books which I show you later, the references. So as Area said, the characteristic foliation of K contact manifold is transverse almost scalar, and the characteristic foliation of a Sasakian manifold is transversely scalar. However, if the characteristic foliation of K contact is transversely scalar, it does not imply that it's Sasakian. So being Sasakian is a kind of a little more complicated property than purely transverse property. So what about some? So you see, when we start with a foliation of dimension P and codimension to Q and smooth manifold of dimension P plus 2Q, and we have a transversal foliation if there exists a cocycle modeled on a Keller manifold N with, let's say, metric G and complex structure N. And then the normal bundle, remember the normal bundle is the quotient bundle of the tangent bundle by the bundle tangent to the leaves of the foliation. So we have a foliated, in this case, we have a foliated Keller structure. Foliated meaning projecting along the submersions. So it's or invariant by vectors tangent to the leaves. So we can simply construct these, you see, J. Sorry, I have to drink something. Metric Riemannian, as you see here, J bar and endomorphism, G bar and J bar endomorphism, almost complex structure on the normal bundle. And that's the way to define it, because on the transverse manifolds, these objects are invariant, Jn and Gn are invariant by the holonomous pseudogroups. These definitions here are let's say, okay, are just well posed because of this invariance. And we have this one, this Nienhuis tensor for the J bar 1-1 tensor of the normal bundle, and it's not. It's almost obvious that it's let's say equal to 0. As a section, of course, it's for the sections. Okay. We define the fundamental to form omega bar by xy by the standard way, and we see that this form is basic, actually. So it's just repeated, and we can repeat everything. So you have here everything step by step. So we have this operator del and del bar. We can define basic Dolbeault homology, everything could be defined, and we have the so-called transversely holomorphic and transversal Keller foliations. They have been studied by Aziz El-Kassimi and published, you see, but his papers are usually in French. So we have the star operator in basic cohomology, and all that stuff. We can go to the Laplacian. We can have a metric on the basic forms with complex values by integrating it. So all that standard stuff is let's say goes to let's say foliated setting, and you can you see there's a foliated. We can also say define a foliated Laplacian. You see Delbar operator. All these you see complexes. You see Dolbeault cohomology at the base. So everything is possible. So everything works nicely, and you have these. You see. Adjoint, you can see with adjoint operator, so it's self-adjoint operator on so-called foliated or transversal elliptic operators. So it's everything is in Aziz El-Kassimi paper, very carefully proved, and you see the Keller form for you see Keller form on the transverse manifold and correspond to the basic 1-1 form. So you can actually all that one can say that for foliated objects, everything you know about objects on a manifold or tensor type objects on the manifolds go to foliated objects. Without, you have to be just careful how to do it, but basically there is no problem, inherent problem. So especially only the only problem could come when you have to integrate something. So that's the only problem, but it is usually can be resolved positively. So there is also, you know, for symplectic manifolds or Keller manifold, you have this operator L, which is a multiplication by the symplectic form. In the case of the Sasakian or transverse symplectic manifold, we just there is this transverse symplectic form to form, so it's basic to form, so you can do it. So you multiply. And by lambda, we have the adjoint using this foliated star operator, adjoint of L. And you know that the main, there is a very nice theorem about Keller manifold or symplectic manifolds, the Hart-Lefschetz property. Probably you are aware that the Hart-Lefschetz property, you see, played a very important role in the search of non-Keller manifolds. There are so-called Lefschetz manifold in which, for which the Hart-Lefschetz property is satisfied. So there was, because in the 80s or 70s, a lot of geometers looked for necessary conditions for a manifold to be Keller. So all these, we see properties, they try to find, check whether all these well-known properties of Keller manifolds were indeed sufficient, or or just necessary. So one of them was a so-called Hart-Lefschetz property. So foliations is also, you can define for, let's say, Hart-Lefschetz property for basic cohomology. So so you have here all these definitions. You have all these properties. And so you have this Laplacian, the standard Laplacian is twice. There's a Laplacian, you see, commutes with L, commutes with lambda. And you have the El-Khatimi proved that the following theorem. We have a transverse Keller foliation on the compact manifolds. The homological orientability is necessary because we want to have the top dimensional group non-zero. In this case, we have Poincaré duality. It's more or less important because it's a Poincaré duality in basic homology. It's very important tool. So we have basic forms. We can, you see, represented as homogeneous forms of type RS. So there is this form is harmonic, alpha is harmonic, if and only if all its components, homogeneous components, are harmonic. So you see the space of basic forms just splits into, basic harmonic forms just splits like that. And in the basic cohomology also, because one can prove in this case that for each basic cohomology class, there is just one representative by basic harmonic forms. And of course, and the conjugacy, you have this one, you see, just gives you an isomorphism. You just interchanges the indices, these homogenic indices. Okay. So I just skip it probably because there's a very nice spectral sequence, but there are abstractions like to being transversal Keller. You see the formality of the basic homology. If someone looks for it, I can explain it later. Massey products, it's also a a little bit more advanced necessary condition, which comes, you see it, from formality. Okay, so it's as I told you, there are many questions. So, for one-dimensional foliation, we can ask questions like, is it Riemannian, transversely Hermitian, transversely symplectic, transversely holomorphic, or transversely Keller? So all these questions, given a foliation, we can ask. Okay. So let's say I can skip it. Okay. So there is this question about how to distinguish K-contact from Sasakian manifolds. So there is a Sasakian version of Hart-Lefschetz theorem given by Capelletti Montana and his collaborators some time ago, some years ago, and he proved that if we have a compact connected Sasaki manifold of dimension 2n+1 with all these, that for any p between 0 and n, the multiplication given by that, eta times d eta to power p, gives you an isomorphism between the cohomology group n minus p and n plus p plus 1. So it's very interesting because for Sasaki, it's not related to being transversely Keller. it's something more. No, it's a little bit different. So, and because it's you do not need to calculate the basic cohomology, but you only deal with cohomology of the manifold. It's also important because when you have a manifold with a Sasaki structure, in principle, you can have on the same manifold many different Sasaki structures. So many different foliations, which are transversely scalar. So to answer the question whether a manifold manifold admits a Sasaki structure, it would be much better to know some condition which involves only the cohomology of the manifold and not basic cohomology, because when you change a foliation, the cohomology, its basic cohomology can be different. Moreover, the basic cohomology does not inject into the cohomology of the manifold, even in the case of Riemannian foliations. So, so it's a very important theorem, which gives you the tool to, let's say, to look for non-Sasaki manifolds. Okay. So actually, in the paper mentioned, you see the authors construct 5- and 7-dimensional manifolds, nil manifolds with K contact, which are K contact but do not admit Sasaki structure. Okay, so using this theorem, because they, you see, what is also important for say nil manifolds, it's that you know its cohomology. The cohomology of nil manifolds is the cohomology of the associated nilpotent Lie algebra. It's a very well-known, a very old theorem. In the case of solved manifolds, so the quotients of solvable Lie groups, it's a little more complicated. In some cases, it's true that it's the cohomology of the associated solvable Lie algebra. So actually, all these cohomological calculations can be reduced to the calculation in cohomology of Lie algebras, which are algorithmic. So you can write a script to calculate it, or you can try to calculate it by hand. Of course, it's well, there's also very nice things that up to dimensional 7. So, for instance, nilpotent Lie algebras have been classified up to dimension 7, as I'm aware. So simply you can look at the list and just check on generators. So you can look and try to imagine whether you can find some property for which you are looking for. So it's okay.
Sorry, Robert, do you know any more results about this Lie algebra? I mean, you commented on the nilpotent case, but semi-simple case or things like that. There are all the properties that are key to obtain these results?
Yes, there are. It is for solvable manifolds. They have been studied by, for instance, Kasui, and this he published some years ago. So it's but it's very technical, really technical. So it's there are also results about Dolbeault cohomology. It's relatively recent, because you can whether the Dolbeault cohomology, you can use the Dolbeault let's say, calculate Dolbeault homology of the manifold, nil manifold, and the Dolbeault homology, kind of Dolbeault type cohomology of the associated Lie algebra. And it's not obvious that it is the same in the case of Dolbeault homology. But there are some results like that, you see, in recent years, yes. Yes, but yeah.
Thank you.
If you have any questions, even after the lecture, just write to me and I will try to answer them. Let's say, give some references usually. Let's say to look, and let's say I can check it whether, yeah. Anyway, all these manifolds, you see, nil and self manifolds, it's a very nice testing ground for any conjectures, because you can compute the cohomology. So it's not so abstract. So you have some relations. So you can write simply write it down. You see, up to recently it was done by hand, but later, well, you can use a script, you see, to calculate. Yeah. So let's say there are a lot of things about it. So what about also, let's say, so the second part I have, so there are, let's say, there's also a way of characterizing, you see, a Sasakian manifold among these almost contact metric structures with all these tensors using special objects, special tensors. One of them is H, which just measures how far phi, this 1,1 tensor, is far from being invariant. So for instance, in a contact metric structure, the Ricci is just like that. The Ricci in the direction psi is 2n, so it's just half the dimension, let's say, minus the trace of H squared. So the contact metric structure is K contact if and only if the Ricci is equal just to 2n. So it's just more or less quite well-known results. You see, K contact is a section, you see, all this very special sectional curvature involving psi is equal to 1. For that, you see the metric curvature tensor is just of this form. So for okay, so it's all this, you have all these little steps. You see a lot of people worked on it, especially Japanese, because Sasaki, as you can imagine, you see, is after a geometer who studied, I believe, the first Z structure, Sasaki. So all that, there were a lot of papers, early papers from the 50s written by Japanese geometers, but I confess some of them are very difficult to read, especially for me, because they are all this, you see, local stuff with a lot of indices and not the tensors written as global objects. So there are, okay, so there are a lot of, what is interesting, perhaps especially for physicists, is that compact K contact Einstein manifold is Sasakian. So it's Einstein condition. It's really is what I would like also here. So as I told you, what I've been interested, or we've been interested in Laplacians recently. So we have two compacts old Patodi result about Laplacians. So we have two compact Riemannian manifolds. If the spectra are equal, spectra, P means the spectra of the Laplacian acting on forms. for zero forms, so on functions, one forms and two forms, just enough. So if these two spectra for 0, 1, and 2 are equal, then the dimension of the manifolds are equal, and both are Einstein if and only if one is Einstein if and only if the second is Einstein, or constant sectional curvature, one is of constant sectional curvature if and only if the second one is of constant sectional curvature. That's a classical result which showed how spectra of the Laplacian are strong tools, actually. So for Sasakian manifolds, there is a version of Einstein. Sorry, I just missed. It's a Sasakian manifold is called Einstein. Sorry, I missed here Einstein here. So if there exists a constant alpha and beta such that the Ricci tensor is equal to alpha g, it's a constant, plus beta eta times eta. So that's you see a Sasakian version on Sasakian. So Einstein condition. So it's a weaker, slightly weaker condition. And you see, it was studied in depth by, for instance, I haven't mentioned yet Krzysztof Galicki, but it could be for you of also interest. I wonder whether any of you met Krzysztof Galicki. He was of Polish origin. He graduated in Poland in physics, but he got his PhD in US in differential geometry, and he wrote a lot of papers, a lot of works, especially on Sasakian manifolds. And Boyer, they wrote a very nice volume on let's say, Sasaki manifolds, a kind of Bible, and published by Oxford University Press. And you see, you can find a lot of stuff about almost everything what is necessary to know about Sasaki manifolds. You see, and in that book. So, and there's a version for Sasaki by Zdzisław Olszak, a Polish mathematician from Wrocław. So
sorry, Robert, you said Krzysztof, it's just what else? Gawinski or?
Galicki. I will show you.
Galicki. Okay.
I will show you the references. Sorry.
Right, thank you.
So there are two Sasakian manifold, compact Sasakian manifold. We have spectra. Dimension is greater than 2. Spectra for 1 and 0. We have the spectra are equal. Then these dimensions are the same. One is eta Einstein, M is eta Einstein, if and only if M1 is so, and M is Sasaki space form with constant phi sectional curvature. See, if and only if the second have the same property. So it's just a version of the Patodi theorem for Sasakian manifolds. Okay, so here precisely you've got the 3 books which I recommend to anyone who wants to go deeper into Sasaki. So we have the Charles Boyer and Krzysztof Galicki book, Sasakian Geometry, from Oxford University Press, published in 2008. And you have the Introduction to Contact Topology, published by Cambridge University Press in 2009. Hans-Jörg Geiges from Cologne University. And you have a Blair book, which is more classical Riemannian geometry approach, Riemannian geometry of contact and symplectic manifolds, published. It's a second version of this book, published in 2010. So it's quite a lot of approach, is tensor approach to contact and symplectic manifolds. And of course, there are K-contact, Sasaki manifolds, everything there. And Galicki also, this Boyer-Galicki book uses the foliated approach. As well, you can find there quite a lot of stuff about 3 Sasakian manifolds, which I believe also of some interest in physics. So it's a very thick book. And I have just here, you will see a lot of additional literature. And so let's finish. Muchas gracias.
Muchas gracias, Robert. Thank you.
And it's a pleasure, a real pleasure.
It was a real pleasure to have you here. So is there any comment, question, remark? Well, Robert, truly speaking, I have many, but just a short one, okay? But yeah. maybe annoying, because as I said, I came up with these Sasakian manifolds trying to study certain physical systems, yeah?
Yes.
Hydrodynamics and things of the kind. So I will tell you something that it is quite shocking to me, because most of the cases I found, or maybe I found, they are not compact, you know?
Yeah.
And the problem is that when you are not compact, many of the results you saw they don't work, yeah? So is there any way to surpass this compacity or something?
It depends what
locally?
It depends what you want. Because, well, certainly all that cohomological stuff will not work, because it's usually based on the fact that that the cohomology is finite dimensional, all that stuff. But yes, but a foliated approach that could be circumvent the lack of compactness. Actually, a lot of results about Riemannian foliations are true under the condition, let's say, the easiest is that the orthogonal geodesics are global. So that's the easiest condition. So a kind of transverse completeness.
It could work. Yeah. Okay.
Yes, it will work a lot of stuff. But it's also, you can weaken it, because actually to prove many things about foliation, you just need that you take a leaf and the geodesic which is orthogonal and starts at the point of a leaf. But you need only to know that when you travel along the leaf, the geodesic of the, let's say, the tangent, this orthogonal vector travels also along this path in the leaf. And you can start the geodesic, but you need to know that it is defined on the same interval as the initial one. That's also enough, because it produces some results which can prove it, but simply it depends what you want.
Yeah, I see. That it's because
because compactness is a very convenient assumption.
Yeah, I mean,
forget about many problems.
Makes life easier. Yeah.
Yes.
Yes.
So in physics, you have the same problem, the compactness, let's say, in semi-Riemannian geometry. Because geodesics are not globally defined.
I mean, for example, from Riemannian geometry and special relativity, general relativity, well, it's something quite common to find these things, and it's not weird. But when you go to thermodynamics, the examples I was studying, it turns out that everything is non-compact. It was something like, how it could go. At least the things that I managed to maybe find, yeah. And I wanted to ask you, because this is from a mathematical point of view, and physically, I mean the Einstein manifolds and things, they are typical cases of this. Do you have any other example or other case that could be potentially be studied by means of this? Have you found anything that it could be worth of remark?
Well, I can think about it. I cannot answer you just like that because unfortunately I know very little about physics. That's the problem. So I have a very good PhD student. Perhaps you met him in Warsaw. Rusbek Mohseni. He was with Grabowski for 2 years.
No, sure, yeah, I think so. I think
yes. He moved to which university, got a position there at the moment, but he graduated in physics actually. But in Iran, yes. So it's so I'm trying to learn something about physics slowly, but I cannot give you some. If you send me let's say a question, I can think about it. But
okay,
I simply cannot answer like that.
Yeah, sure.
It would be just guessing. Sorry.
It's a curiosity. You gave a very interesting talk, so I'm very thankful for what you did. Please send me the slides as you said.
Yes, certainly, I will send you.
Because I took a look at your.
I have two comments.
Once, sorry.
Here is Manolo. I would like to put two comments in the.
Okay, yes.
Related with your. Okay, Robert. It's a pleasure to meet you.
Manuel.
Muy bien. One is respect to the calculations of these homologies. For nilpotent groups and solvability groups, you can quotient the group by lattice and you obtain a compact nil manifold or a compact solvable manifold. And so there is a theorem by Nomisu and another theorem by Atori, and you can calculate. The theorem says that the cohomology of the manifold is just isomorphic to the cohomology of the Lie group, of the Lie algebra. And so for this reason, you can calculate very easily all these cohomologies. We use this in many papers just to calculate cohomologies, Betty numbers and so on. And concerning the compactness thing, so the main application to thermodynamics is just these contact metric structures, and you can follow this mini course that Alessandro Bravetti gave in our annual meeting in Sevilla in this fall workshop, and this is published in International Journal of Geometrical Methods in Modern Physics, and there is a lot of things about this Sasakian and other things just to apply to thermodynamics. Of course, as you say, the model is not compact, of course.
Yeah, that is there. And when you try to generalize to other things, it gets only worse. But some of the things maybe they can be potentially used. I will take a look at it. I'm curious indeed.
Because one of the objectives in differential geometry is to study these manifolds, but with no applications in potential applications. So just to know the topology and the curvature properties of these manifolds. But of course, at the end, there are applications.
Yeah, sure.
And Manuel, can you send me the reference of this paper?
Yes, I will send you.
Great, thank you.
I worked a lot in these things, but many years ago with Luis Cordero and Marisa Fernandez.
Manolo, I think that I know what you are talking about, Bravetti, but send me just in case, because I don't know if I'm sure what you are talking about.
I will send you.
Thank you.
I will send you. There was a mini course, it was a long paper about, I don't know, probably 50 or 60 pages. And he developed all the machinery to study thermodynamics using contact geometry, but contact metric geometry, which is a difference because we call contact and we are not considering metric Riemannian an adapted Riemannian metric, but because we are not interested in this case, but for it's
physicists,
important
it's
to have this
important.
Riemannian.
Yeah.
Yes, it's important.
Okay. So, well, is there any other question, comment, remark to our speaker? No? Okay, so Robert, thank you very much for your talk. It's been a pleasure. If you are invited to attend, and if you will be in Warsaw, just let me know. Okay, maybe
Yes.
we can talk for a while. As I said to you, I have a lot of teaching this semester, but Fridays are essentially my free day, more or less. Yeah,
Okay.
but I said
Great.
it would be nice to see you.
Yeah, nice to yes, me too. Yeah.
Okay, so
Gracias. Thank
Bye-bye.
you.
Gracias.
Thank you for the invitation. Bye.
Hasta luego, Robert.
Hello.
It's been a pleasure. Sure.
Placer.
So within a week we have another talk. This time is by myself because I wanted to take the chance of giving a talk after getting my PhD the 23rd of October. Indeed, it was 16 years ago. So I had a lot about the integrable system, value system. So I will make yes a review of that in case one of the topics I was interested in. Okay, so see you in a week, and thank you very much, and I hope to see you again.
Thank you.
Bye-bye.
Bye.
Thank you.